Okay, so let's look at some practice problems. Now, an example Ka from pH. Okay, so let's think about this. If we have our pH, we can get to our hydrogen ion concentration when we're at equilibrium. Let's see where we can go with that. So this gives us a Ka of an example compound. That example compound is the B vitamin niacin. Now, a 0.020 molar solution of niacin has a pH of 3.26. What is the acid dissociation constant for niacin? Find the percent dissociation. Okay, so we got to work through a couple components of this problem. Now, the first thing that we need to do is recognize our compound, our acid. We can look at our acid as HA, and that dissociates, that breaks down into H plus and A minus. Okay, now I'm going to set this up as an ICE table, ICE, because we're given our initial concentration. Now, I'm going to go ahead and say my initial concentration of HA is 0.020. My initial concentration of my hydrogen ions is effectively 0, and that is 0, so 0 and 0. Now what I know to happen is that this HA will dissociate, so that will be minus X. My hydrogen concentration will go up by a factor of X, and A will go up by X as well. And at equilibrium, I will have an HA concentration of 0.020 minus X, and a hydrogen ion concentration, which, well, that's X. But actually, I know my hydrogen ion concentration at equilibrium. And that is because I know my pH is 3.26. So I can say 10 to the negative 3.26 to figure out my hydrogen ion concentration. Now I'm going to pause the video, and then I'm going to continue it because I came up with, on my other screen, my hydrogen ion concentration 5.4 or 5.50 times 10 to the negative, that would be 4 times 10 to the negative fourth molar. Okay, so at equilibrium, this is 5.50 times 10 to the negative fourth. And then that means A is also 5.50 times 10 to the negative 4. Now, what this also gives me is I know that that is the amount of hydrogen ion, and I can go ahead and say I know my HA, 0.020, that's my initial concentration, minus 0.000550. I can plug that into my calculator as well, and I can figure out that 0.02 minus 0.000550 is 0.01945. So that's my HA concentration. Now I want to find out what my Ka is, so I can say Ka is equal to 5.50 times 10 to the negative fourth squared divided by 0.01945. Okay, so there's a little bit work left to do in this. I'm going to go ahead and plug it into my calculator. 5.50 exponent negative 4. I'm going to square that, and I'm going to write this one out. That's 0.12345 divided by 0.01945. And I'm going to call that 1.56 times 10 to the negative fifth. And that's my Ka value. Okay, that's good and that's great. What is the acid dissociation constant? solved. So I'm going to say check. Now find the percent dissociation, percent ionization. Okay, so for the percent ionization, what I need to do is I need to take into consideration this concentration right here and this amount right here. Or sorry, I need to take into consideration the hydrogen ion concentration and my initial HA concentration. So for the second part of the problem, I'm sorry I'm all over the place on this, but I'm going to say this is going to be 5.5 times 10 to the negative fourth divided by 0.02. So I'll plug that in. 5.50 exponent negative 4 divided by 0.02. That's multiplied then by 100, and I get this is 2.75% ionized. So if we go back to our definition of a weak acid was about 1% dissociated. Okay, this is about, well, it's nearly 3% dissociated. So we're talking about a relatively strong weak acid. Okay, now this gives me my Ka 1.56 times 10 to the negative fifth. That's great. Let's remember that. Oh, pH from a Ka. The Ka for niacin is 1.5 times 10 to the negative fifth. Is that pretty darn close to what we just solved for? It absolutely is. Okay, so now let's use this. So this is just kind of a good, we did it right. Now, what is the pH of a 0.01 molar solution of niacin? Find the percent dissociation. Okay. Now, we've got a 0.01 molar solution. I'm going to set up my ice table. HA will dissociate into H plus and A minus. ICE. I got 0.01, 0, 0, minus X plus X plus X. 0.01 minus X, X, X. Okay. Now what I need to figure out is my hydrogen ion concentration. Now this Ka value is just like any sort of equilibrium expression where you get to a point where you're like, can I ignore, or am I going to have to do the quadratic equation? And this, I would argue, is small enough that we can go ahead and ignore, or we don't have to do the quadratic. What that means is that we're going to set up our Ka expression. Ka equals H plus, A minus, and HA. Okay, so this is equal to 1.5 times 10 to the negative fifth is equal to, well, HA, and that is going to be, or sorry, H is going to be X, A is going to be X, HA is 0.01 minus X, but I'm just going to ignore this minus X. So I'm going to write that as 0.01. Okay, so now what I've got is 1.5 exponent to the negative fifth times 0.01, and that gives me an even smaller number, and that is going to be, I'll write this out, is 0.000015 equals x squared. So I can take the square root of both sides, and I'm going to get x is equal to 3.87 times 10 to the negative fourth. Okay, so that x is, well, that's my hydrogen ion concentration. So I can now type in negative log of 3.87 times 10 to the negative fourth, and that will get me a pH of 3.41. Okay, so there's my pH. Now the next part of this was really, what is my percent dissociation? And that's going to be my hydrogen ion concentration, which is 3.87 times 10 to the negative fourth, divided by 0.01, because that was my original AHA concentration. Multiply this by 100, and I get that 3.87 exponent negative fourth divided by 0.01, and I get multiplied by 100, and I get 3.87%. Now chances are my numbers could be a little bit different if I did the quadratic, but I'm going to go ahead and stop there.